energy band diagram. We are going to continue with that, and today what we are going to do is we are going to talk about more about Schottky junction. Okay, so it will be the energy band diagram of a Schottky junction. Okay. So if you remember the other day, I told you what exactly do we mean by Schottky junction. By Schottky junction, we are talking about a metal semiconductor junction. Okay, so that's important. So we need to know the definition, and we can actually start from there. So as we have seen in the other class, that what we do usually is we basically start with uh, the energy diagram or energy band diagram before we really combine them together. Okay, and after combining, how does the electron flow? That is what the band diagram will actually tell me all about. Okay. So what we are going to do now is we are going to draw a figure, which is actually important, just like the last class. Okay, and then I'm just going to explain as I'm drawing the figure. Okay, that is very important. So what happens is that whenever we are talking about something like a conduction band or a valence band, okay, it's like you have the electrons free in that particular region, right? So let's say this is the zero level. Okay, so that means that if we have the electrons above this level, we are going to have the electrons free, and it will be actually free to conduct. So whenever you basically have any kind of metallic system, you basically have the conduction band present. Okay, so if I just draw a metallic band, let's say I'll just take this. Okay, so this is before the uh, contact have been made. Okay, this is before the contact. So this is the metal that we are talking about. Okay, so we have got certain thing which is termed as work function. That means that I need to provide some energy to a system so that the electrons can actually get free and actually can get start conducting. Okay, so that is exactly what is work function is all about. Okay, and that means that I need to apply this much of energy so that the electrons are free to move around, right? So this is something which we can write down as E phi m. Okay, so here what I can do is I can write it down as E phi m. Okay, so here m basically stands for metal. Okay, so m here stands for metal. Okay, just keeping the notations clear. Okay, and then if someone tells you what is E phi m, E phi m, okay, this is nothing but the metal work function. Okay, this is metal work function. Okay, so work function is something you might have heard about even in let's say for example photoelectric effect and all. Okay, so these things are quite common. And then how much is the work function for certain material, that also I think we know some typical values. Okay, so if I write down typically, okay, what we can do say is that this work function will be approximately 4.4 EV. Okay, for some metals like let's say aluminum or silver. Okay, this is the work function that we have. Okay, so you can just go and check. I'm just writing down the approximate values here. Okay, or might be we have some other values. Okay, so these values are important because this is actually define a lot of things about the property. Okay, what is the property of that material, how it can be used, all those stuffs. So for gold it might be approximately 5 EV. Okay, and then we can go a bit further, and then we can talk about, let's say, 5.7 EV, and that's for, let's say, a metal like platinum. Okay, so these are some typical work functions that we have. Okay, now the thing is, how does the semiconductor looks like? Okay, so for semiconductor we can again draw a energy band diagram. Okay, so separate, it is before. Okay, we are not saying that we have made the contact as yet, so just before the contact. So let's say this is the conduction band. Okay, and we have to draw the Fermi level. So I think I can take a separate color. This is the Fermi level for the semiconductor. Okay, and then we of course have the valence band. Okay, so we have the valence band. So this is how a typical semiconductor energy band diagram will actually look like. Okay, and then there are certain things that we should know. This is the gap, so that the electrons are getting free, okay? And let's say the electrons are here, okay? Let's say we have the electrons here, okay? So electrons are there, and if there are electrons in the conduction band, there will be holes in the valence band. That also we know, okay? So what we can do is we can just probably just level them, okay? We'll just level them. So this is your EC, okay? The conduction band. Okay? And then we have got the Fermi level, right? So might be we'll have EF, okay? So this is your Fermi level. And then we have got the valence band, right? EV. So whenever you are doing it in your exam and you are being asked, it's very important that you please draw the figures very clearly. It's important because that will carry a lot of marks, okay? And then this particular term, okay, this particular space, I think I should just take an arrow here. This can be actually written as E chi, okay? And then this E chi is actually called the electron affinity, okay? I'll just write down that. And this is the work function for the semiconductor, E phi S, okay? So here S basically stands for semiconductor, okay? Semiconductor.
Sir.
Yeah.
Sir, yellow line represents the metal, na, sir?
Yeah. So what I'm saying is that if we have an electron actually going into this yellow line, the zero line, we can say that it is totally free. Okay.
Yes.
So it's totally free. That means it is free for conduction process. Okay. So I'm just representing it here. I'm not really connecting it with the semiconductors right now. Okay. But we are saying that this is the distance that it needs to cover so that it can become totally free. I will just draw the entire figure on the other side. When we make the contact, it will be a bit more clear. Okay. So let me just complete this first. So S basically will stand for semiconductor, okay? And then I can just, I think I should mention this. This is important. These are the terms that I should know, okay? And then this is E phi S. Okay. So what is my E chi? My E chi is basically called as the electron affinity. Electron affinity, okay? Important. And the other term E phi S, okay, it's actually the work function of semiconductor. So you know, whenever you are actually interested in making the charge carriers free, you need to apply some kind of energy, okay? And what energy you are providing is basically nothing but in terms of the work function. Okay, so we have got the work function of the semiconductor. So I think I should just make it small. This easy. Okay, so we lack of space here. Okay, so what work function of semiconductors, and then there are some typical values for work function of semiconductors also. Okay, so let me just write down some typical values that we should all know. One is, let's say, 4.2 EV, and semiconductor is not that it should be just pure semiconductors, right? There are a lot of applications for different kinds of semiconductors. So gallium arsenide is one of the most popularly used semiconductors, okay? And then we have got, let's say, 4.3 EV. I'm just going randomly, okay? For let's say indium phosphate, okay? And then we can have something like 4.0 EV for silicon, okay? And then we have got 4.1 EV for germanium. If you want to have an electron totally free, if you want to have that uh, uh, free electron in case of, let's say, gallium arsenide, you have to apply an energy of 4 EV, and then this will actually overcome this, and then they will be totally at this particular level. Okay, so this is important because you are combining electron, I mean metal and semiconductor, and talking about the Schottky junction, and that's the reason that we need to study this. Okay, this is important. Okay, let me just draw the figure when we actually combine. Okay, and we will see that it is not as simple as it looks. Okay, so what I'm going to do now is I'm going to draw the combined level. Here we need to notice one more thing. I think that is also important. You see this gap here, okay? So if we just take this, probably I can just draw a few lines here. So see, there is a gap here, okay? There is this gap, okay? And this gap is basically nothing but a kind of discontinuity, you can say, this gap. Okay. So you have for metals, see, forget about valence band right now. For metals, you have this metallic surface, and then the electrons are actually needing this much of energy so that it becomes totally free. But then these metals already have a lot of free charge carriers. Okay, it's already there, and that is why they are conductors. Let's say, for example, copper, silver, gold, and so on. Okay. And for a semiconductor, a similar behavior is observed just like metal if we have the electrons which are there in the vicinity of the conduction band. Okay, so if we have electrons near the conduction band, that means they are almost free and they are in the process of they are actually assisting in the process of conduction mechanism. Okay, so you see there is a gap here. We have this gap. For metal it is here, for semiconductor it is here. And if you basically consider this as an energy scale, you know at a lower energy we have the electrons free in metals, but for semiconductors this energy is slightly higher. Okay, that is the fundamental difference between metals and semiconductors, because you know in metals there is no such concept as valence band or conduction band. They usually overlap. Okay, so on the top of this is nothing but comparable to the conduction band of the semiconductor. So this is the discontinuity that we talk about. Okay, and then this discontinuity, let's just write it down by, okay, so this discontinuity we can just write it down as E phi b, or let me write it down small b. Okay, E phi b. So this is the discontinuity that we have. Okay, so maybe I can just write it down this here. Discontinuity. So I hope you understand why I'm calling it as discontinuity. Okay, because the behavior of the electron on top of the valence band of the conduction band for a semiconductor, okay, will be similar to the behavior of the electron at this level of metal. Okay, and so this is a gap that is there, and that is basically called the discontinuity. Okay, so now we are going to see what happens after we actually combine the two system. Okay, so just give me some time. Let me need to draw it right. So I'm not just drawing in comparison with this. Okay, I'll just draw it like this. Okay, just take a lesser space. So I'll draw the metal on one side. So once you know what happens or how does the band energy band looks like when they are not combined, you can easily draw it when they are actually combined together. Okay, so you know there is a discontinuity here. So I think I should take the straight line. You see, yeah. So we basically have a kind of discontinuity here. Okay, and then when you're combining, what happens is the Fermi level are actually going to be at the same level as of the metal. Okay, if we are actually considering the conduction process. Okay, and then what happens is, I'll explain this term now. Okay, and where are the electrons? The electrons are here for the semiconductors. We have combined them. Okay, and let's just say that we have made the junction, but we have not applied any kind of potential. Okay, so the electrons are here. Okay, and if as I said that if this is the band gap, here also the band gap will remain the same. So there are no chance that the band gap will be modified when you combine metal and semiconductor. So if we say that the conduction band is actually getting bent, okay, so this is EC, the valence band will also get bent because this gap needs to be the same. Okay, so it is bending. Now just let's have a look at this diagram and try to understand one thing. Very simple. Okay, you see this gap, this bend that is being shown is actually representing the depth of the potential well. So if you all remember quantum mechanics, we say that the concept of, let's say, quantum mechanical tunneling, okay, or the depth of the potential well and so on. Okay, there we try to understand that if we have an electron trapped within a system, is it possible that it can come out of the system? Okay, so we have to give that much of energy so that it can come out normally, else there has to be the process of quantum mechanical tunneling. So this band that is being drawn here is actually representing the depth of the potential well. Okay, so if I don't consider these electrons, okay, maybe I should not consider these part. Okay, this let it be very plain, and we don't have any electrons which can actually just come out of it because everything is below this depth. So what happens is that if we apply some energy, then only the chances are that this energy level will be raised and the electrons will also raise, and as a result, the electrons will flow from the semiconductor to the metal. So idea is very simple, and that is the basic logic behind what is say we can say the conduction mechanism that happens when we actually combining a semiconductor and a metal. Okay, so this is my band gap. Okay, and that is the depth of the potential well. So this is, let's say, Eg. We usually represent it by Eg, if you remember. Okay, we usually represent it by Eg. So this is how you draw the band diagram for this. Okay, and here we are saying that we really don't know whether the electrons can actually conduct or not. Okay, because we have not applied any kind of potential. Now what we are going to do is we are going to give some kind of potential to it. Okay, so how much barrier it should overcome. Okay, and that is what we call as the Schottky barrier. Okay, so you see this. Okay, this might not be up to the scale, but you see if you combine these two, you need see this much gap is already there. Okay, and this gap is actually called the Schottky barrier. Okay, so I'll just write down this term. Okay, so let me write it down here. E by S. Okay, this is called the Schottky barrier. So that is the discontinuity. Okay. Okay. So how can we calculate this? This is very simple. You see this here. E phi b. Okay. E phi b is actually nothing but E phi m, this total distance, minus this E phi s, right? So this will be this distance of E phi b. So if we just want to write down E phi b, we can just simply write it down as E, and then we can just simply write it down as phi m minus chi. This term is typically called a Schottky barrier. Okay, and the value will be typically 0.6 to 0.8 EV. Okay, for what? It's basically for N-type silicon. Okay, plus metal. So the term, as soon as I'm using the term Schottky, straight away I'm saying that there is a semiconductor and a metal junction. Okay, so this is 0.6 to 0.8 EV and 0.7 to 0.9 EV. Of course, depends on the doping, but we are just writing down the typical value. Okay, this is for, let's say, gallium arsenide plus metal. Okay, so this is the
Sir,
typical value of the Schottky barrier. Yeah.
sir, is it same as the band gap between band gap between EC and EV?
Not really, not really. See, you see, look into this diagram. Okay, it's comparable. It's in the same range. Okay, if you remember, for something like germanium or silicon, the band gap lies between 0.7 to 1.1 EV. Okay, but you see here, if you look into this diagram and look into the Schottky barrier, you see that this Schottky barrier is E5B. Okay, and band gap is this. Band gap is this. This is the band gap, right? So you see there is slight difference there. Okay. So why does this Schottky barrier come into the picture? Because whenever you are combining a metal and a semiconductor, it's not that the semiconductor has to. There are already, see, whenever you apply some kind of biasing, the electrons are already there in the conduction band. So in the
Yes, sir.
last class, we have seen that whenever we have got two different semiconductors and we want to combine them, when we combine them, the Fermi level comes together and the electron starts flowing from a region of higher concentration to lower concentration until and unless they become equal. Okay, so you can say that it's comparable to the band gap, but definitely no, it's not the band gap. It's not the band gap. Okay, and that's why I have drawn this figure. So band gap is Eg, which will be greater than E5B. Okay, so an interesting question would be what happens when Eg and E5B are comparable. Okay, but before that we need to understand that in this particular figure, if Eg is the band gap, this is always greater than the Schottky barrier. Okay,
Sir, then what is Schottky barrier then, sir? Sir, how
yeah,
we define Schottky barrier then?
yeah. So you see, what happens is that if you are actually going to combine the metal and the semiconductor together, and we want the electrons to flow from the semiconductor to the metal, it has to overcome certain barrier, right? Potential barrier, as far as quantum mechanics is concerned, right? So how much energy should we actually put into the system so that, or let's say if we want to forward bias the system, how much forward biasing should we do so that the electrons can actually easily travel from the semiconductor to the metal?
Okay,
Okay.
sir.
So
Sir,
in
not
that
from the
case,
valence band, sir.
uh-huh.
Sir, from semiconductor to the metal, sir. Na?
Yes, yes, from the semiconductor to the metal. The interesting part here is that the metal already has got some free charge carriers, right? But then the semiconductor does not have a free charge carrier. So whenever you are doing any kind of biasing to a metal, you already have the free charge carrier. It does not need enough energy. But when we are combining the semiconductor and the metal, I have to look it from the semiconductor point of view because the semiconductor needs that biasing. Okay. So what I'm going to do now is I'm going to draw another figure. Okay. And I think it will be even more clear to you. Okay. So what I'm going to do now is we are going to do biasing. Okay. So let's just do the biasing and might be this will make the concept even more clear. Okay.
Sir,
So let me just take a new
sir,
page. Yeah,
sir, sir,
yeah,
सर ई का भी कोई बैरियर है क्या सर?
yeah. E5B is actually basically a kind of barrier that we have, and that is why we call
Okay,
it as the Schottky barrier. And
ई
Schottky, by the
काय
term E chi,
ई काय
okay,
ई काय इलेक्ट्रॉन
E chi. This one,
is it barrier
this.
sir?
Yes. So this is a good question. And do you know the definition of electron affinity?
No sir, I'm not.
So what happens is if you want to make an electron totally free and you does not want it to be attached with any kind of semiconductor, let's say the semiconductor has got some kind of affinity towards electron, right? Even if it is in the conduction band, it is present in the semiconductor, correct? But
Yes sir.
then, but if you want to make it totally free coming out of the semiconductor, let's say for example, photoelectric effect, correct? A photoelectric effect
Yes
actually talks about an electron coming out of the metallic system, correct?
yes
So
sir.
it has to overcome that barrier. So what happens with electron affinity is that the electrons will be on the surface of the conduction band of the semiconductor and it will be in the process of conduction. But then if you want to totally take out the electron, you have to add some additional energy, and that is E chi. That is called, which is
Sir,
called as the electron
like
affinity.
work function, sir. Sir, like
Yeah,
work
you can
function.
call it as yeah, just like work function. Okay, but it will become totally free from the semiconductor. Okay.
Yes sir.
So that is why we actually need something which is called as electron affinity. Okay, so that term is something which is new, not taught much. Okay, so but this is important from this syllabus point of view. Okay. Okay, so what I'm going to do now is let's do biasing now. Okay, let's do a bit of biasing. So what happens in biasing usually is we can actually either do a forward biasing or a reverse biasing. Okay. So what happens in case of forward biasing in the case that we have seen? I'll just draw one more figure so that it becomes a bit more easy. Okay, so in case of forward biasing, the electrons will rise. Okay, rise to flow to metal. Okay, and if we draw the figure, I think this will be more clear. Okay, so what you can do now is I'll just go back to the previous page here. Okay, and then maybe I can take up this diagram. Okay, so I really have to check the selection tool. I hope it works. So this is the first time I'm using this tool, so that's why sometimes it's confusing. Okay, anyway, can we copy this? Okay. Yeah, that's good. Okay, so I copied this so that I can actually draw this biasing figure again. Okay, so I'll just get back to this. So we have this figure after, okay, after we have combined the junction, and let's do a bit of forward biasing now, okay. And let's say this is a n-type semiconductor as we have seen. So I will just do the biasing. See, the biasing, this is not the right way to show, of course, because I'm not showing any kind of circuit getting completed, but anyway, I'm just doing it so that we all understand this, okay. So I'm just doing the biasing part here, okay. Okay, suppose let's say we have done this biasing, okay, and this is forward biasing. So this is forward biasing. Now what happens is that this level that we have, let me use a different color. Now this level that we have is basically this rises. If this rises, the electron which are there also rises. So what happens is I'm raising the potential, that's all. This is just a way to represent, okay? It's not like you cannot explain it in sentences, but then when you draw the figure, you have a better way of explaining it, okay? And once this happens, you basically have the electrons flowing, okay? And this basic term that the electrons that we are having is basically termed as thermoionic emission. Thermoionic emission. And now we also have the electrons flowing from the semiconductor. Okay, so semiconductor will start behaving better. Okay, because we have more charge carriers there. Okay, now this is the case for forward bias. Okay, what exactly happens in reverse bias? Okay, so if we just go for the reverse bias case, we will see that the current that we are actually talking about will get restricted. Okay, so in general, if we just consider a normal figure here for forward biasing, maybe I can just draw one more figure here. Okay, so we have this junction. It's just like a PN junction that we are making. Okay, on one side we have got the metal. Okay, so on this side we have the metal. Okay, this side we have the metal, and this side we have got the semiconductor. Okay, and then what we do is we just do the biasing there. So biasing is important when we're talking about forward biasing, and reverse biasing is important in case of the semiconductors that we're talking about. So this is the part that we're doing. This is something which we are doing. On top, we are actually showing the figure. Okay. So on top, we are actually showing it. How does it look in terms of the energy band diagram? Okay. So this is the semiconductor, and this is the metal. And since we are talking about forward biasing, so we can say that this is actually nothing but an N-type semiconductor. In a similar way, we can also do the p-type semiconductor. The band diagram will look different. Okay, so if we just think about it. Okay, what happens in case of reverse biasing? Okay, so for reverse biasing, what happens is the current actually gets reverse restricted. Okay, reverse bias, the current is restricted. But then there is a very important trick here that we need to understand, which is basically called as the quantum mechanical tunneling. Okay, so maybe I can just paste that figure again. Okay. Okay, so here what happens is this: you are reverse biasing it. So you know that in a semiconductor, if you are doing any kind of reverse biasing, the width of the potential barrier increases. Okay, so that means that the electrons which wants to flow, let's say electrons are the majority charge carrier, if it's an N-type semiconductor, the electrons that wants to flow from one end to the other end, it becomes more difficult for it, and as a result, you are going to get a very less current. Okay, so you'll be having something like this. So this reduces. Okay, this is reverse bias. So maybe I can just to make it a bit different. Okay, this is reverse bias connection. Okay, and then here also we can actually do the biasing. Okay, so reverse bias. So this will be this. Okay, so this is reverse bias. So we have a reverse bias connection now, and this has dropped. So that it's very difficult for the electrons to flow from this end to the other end. Okay, but then there can be something which we call as tunneling. Now we are actually going into the quantum mechanics part. Okay, tunnel electrons are possible. Tunnel electrons are possible now. Are possible. Okay, in reverse bias. So if you know, there is something which we call as the tunneling current. Okay, there is something which we call as the tunneling current, and that is there. Okay, it's possible. So tunneling current. Okay, so on what does this tunneling current depend? That is also a very important question. Okay, if you understand this, let me just zoom into this picture. Okay, I'll just zoom into this picture and try to explain it better. Okay, so what I'm going to do is going to draw another figure. Okay, let me just make one more page. Okay, so let's say, let me not take the metal part. I really don't need it right now, but anyway, I can just keep it here. Okay, this is the metal part, and what we have here is let's say I'm talking about only about reverse bias right now. Okay, I'm just talking about reverse bias connection. So I'm not drawing the original figure. This is the reverse bias, and this is what is happening. Okay, and let's say just to keep the drawing complete, I can just draw the valence band also. So this is my conduction band, and then in reverse bias, what happens is the electron has to overcome this much distance, so it becomes a very big task for it. Okay, but then if it wants to tunnel through it, it has to cover this much distance. So if you remember your tunneling idea, you have this and it will actually tunnel. We actually show it in the form of wave. So this is the barrier width. So let's say if I write down this as D, this D in reverse bias. Okay, this is reverse bias, let's not confuse, let's not get confused here. Reverse bias. Okay, so D is the barrier width, not the barrier height. Okay, it's the barrier width. Okay. So if you remember this again, okay, I think this is again important. Let me just write down one note here. Tunneling probability, okay, is inversely proportional to barrier width, and that's logical, a bit of common sense also, of course, right? Whether an electron will tunnel or not to add to the current will depend on how thick the barrier width is. If the barrier width is more, the tunneling probability will be less. If the barrier width is less, the chances are that the electron can tunnel from one end to the other end. That's basically the entire concept of the tunneling current. Okay, so the tunneling current actually depends on how thick the barrier width is. Okay, so what we basically can conclude from here is this, that we have to reduce this tunneling barrier. Now, can anyone tell me how do we reduce the barrier width? We have a reverse bias semiconductor. Forget about this example. We have got a semiconductor where we have connected it in reverse bias. Okay, and but we need more current. Okay, so what is the solution we have for getting more current in reverse bias? Can anyone tell me if anyone remembers the idea? Okay, so we basically have to reduce the barrier width, right? Reduce the barrier width to increase the reverse current, right? Increase the reverse current because we are connecting it in reverse bias. So whatever we are getting is reverse current. And how we are getting the reverse current? The reverse current is a result of reverse current is basically a result of tunneling current. Okay, so what we do usually is dope it heavily, if you remember. Okay, so see, your semiconductor idea is very important. Okay, by heavy doping, to please remember these things. Okay, so if you want to reduce this barrier width, we have to do the doping part very heavy. Okay, so we have got two kinds of current that we have actually just now studied. One is the forward current. Okay, so let's say forward. Okay, so what is the forward current? That means we are actually forward biasing the system. Okay, and the forward current is actually a result of two parts. Okay, we have got thermo. Question to you is why we call it thermoionic. You have to recall some of the concepts that you might have already studied. And tunneling. You know, in reverse bias also, the forward bias also, the chances are that you will get some tunneling current. Okay, because if we just go back to that previous figure. Okay, if we just go back to this figure, see here, when we go for the forward bias, yeah, when we go for the forward bias, there might be some electron which is at this level, and then the chances are that there might be some tunneling here also. Why? Because you know the tunneling width will be lesser when we are actually going for the forward bias, but still there might be some kind of tunneling current that will flow. Okay, so in forward bias, the chances are that there will be tunneling current as well as the thermoionic. Thermoionic emission basically contributes maximum. Okay, and the tunneling current will basically be lesser in number. Okay, so that's what we get from the forward current, forward biasing. And if you go for reverse biasing, okay, the main uh, contributor of the current is reverse. The main contributor of the current is tunneling. So that's important. So this is the important part where we need to understand about Schottky junction. Okay, we need to understand that how does the energy band diagram look like when we are actually combining two semiconductors and metal and a semiconductor. Okay, so the energy band diagrams are very important. If you are doing any kind of study in electronics, and if you're going through energy band diagram, you look into these figures. Okay, deep the potential well is, okay, how thick the barrier width is, and so on. Okay, so that is why I've explained this totally, so that everything becomes more clear to you. Okay, some of the new terms that you should come across, you might have come across, is electron affinity. We don't come across it this regularly. Okay, and then work function of semiconductor. Semiconductor also has got a work function. Okay, that is very important. Okay, and then when we combine them, we have got something which we call as the Schottky barrier. Okay, so in your exam, the question might be, how does the energy band diagram look like for a Schottky junction? What is a Schottky junction? Okay, and then how does the electron flow from the semiconductor to the metal when the system is forward biased or the system is reverse biased for an N-type semiconductor? Okay, so you have to do this. If I ask you P-type, again, I'll just give you it as a task, but don't worry, you can actually just search and you can find the answer very easily. I'll explain it someday. But then I think I just leave it to you to do the P-type material. I'll just explain the N-type material. Okay. So please remember all these figures. Okay, this is very important. Okay. So this is where we stop. Okay, and these values are also important. Okay. See, this is also interesting. Typically, when we are actually going to free a electron from metal, the work function is nothing but around 4.4 eV. Okay, but comparatively look into semiconductor, its values are less. Why? Because you look into this, the conduction band is actually above the surface of the metal. Okay, so see, this diagram is not up to the scale. Huh? Please don't blame me because I have not drawn it up to the scale. Okay, so if you draw it up to the scale, probably this conduction band should be slightly lower. Okay, but then above the surface of the metal. Okay, so this surface, basically the metal has got free electrons, and for conduction band we have got the free electrons here. So for the electron to get free from a semiconductor, the energy needed will be lesser compared to a metal. Okay, of course the materials are not same. Okay, but then if you just look into the range, let's say for example platinum, you have platinum, you need 5.7 ev work function, but then if you take something like germanium, it's 4.1 ev. Okay, so that much less energy is needed to make the electrons totally free. Okay, so this two actually has got a very good connection, so you can easily understand it from these two values. Okay, so just look into the values. So these values actually explains a lot of theory. Okay.